Well, our Foucault pendulum has stopped swinging. So, Houston, do we have a problem? Has the Earth suddenly stopped rotating, sending us here in Houston, Texas at about 30 degrees latitude, hurtling towards Florida at about 900 miles per hour? Wait, which way's east? At the equator, it would be about 1,040 miles per hour because rotational physics is fun. So no, our very, very spherical Earth has not stopped rotating, as evidenced by our aliveness. So here's what's going on with our Foucault pendulum and a very trimmed down version of how these pendulums work and why they are important. Since perpetual motion isn't a thing, despite what your IG feed might tell you, every pendulum on Earth needs a little nudge to counteract mechanical friction and air resistance. This nudge, for our pendulum at least, is actually a slight electromagnetic tug on a metal collar at the top of the 61-foot, 7-inch cable itself. The electromagnet is actually a circular ring, triggered at the ends of the 7-ish second total swing, or period, technically. Since it's a ring magnet, it only tugs in the same direction the cable arrives. It does not alter the direction or inertia at all. This mechanism simply maintains the momentum of the 180-pound mass against friction and wind resistance. It's very slight, but it's there. And well, in our case, this mechanism has stopped. Because like all mechanical things, it needs maintenance from time to time, especially after literal decades of virtually non-stop operation. A well-deserved spa day after nearly 50 years of work. Many of us have lifelong memories of it swinging, so it's kind of poignant, if not actually a little bit fascinating, to see it stationary. But I assure you, it will definitely swing again. I mean, right now it's kind of like Hakeem Olajuwon just sitting at half court. Ask your parents about Hakeem Olajuwon. So why are pendulums important? In summary, because when you see the swing change direction throughout the day, evidenced by the pegs being knocked over in a circular perimeter, the pendulum is actually not changing direction. We are. The swing direction does not change. It is the Earth rotating underneath the pendulum. And we are on the Earth, so from our perspective, it looks like it's changing direction, but it isn't. Now I'm gonna knock the rust off of my high school French, which came in very useful in South Texas, by the way. Hi, Miss Lugier. You were wonderful. This experiment, invented by Jean-Bernard Léon Foucault, did I do all right? Any native French speakers want to let me know in the comments? I probably butchered it. It was used to demonstrate way before space travel that our blue sphere was in fact rotating around a wobbling axis. Sphere, ball, globe. Let her rip in the comments. Check the related video, description, or pinned comment for that matter for a much more in-depth video explaining the Foucault pendulum. But with that, y'all are awesome. Take care. Almost ripped my jacket.
You guys catch all that double speak? So the Foucault pendulum alone can't detect anything. That's set in motion, driven electromagnetically. And then he said, well, the magnetic drive motor for the Foucault pendulum, it really doesn't alter the inertia, but it alters the momentum. Don't worry, it's totally not moving the pendulum, but it is. And don't worry that it stopped, because we know that Earth actually moves without it, because we would all be dead if it weren't moving.
And what about all those Foucault pendulums that don't work properly?
Yeah, right?
Didn't they take one in to the South Pole and it spun the wrong way?
Yeah, and that reminds me, that link is floating around somewhere out there in the wild. We need to find it and send it to the web archive and screen capture. I know I did it once upon a time ago. I can't find it though. And I think it wasn't not even just like once. Like they set it up a second time and they still couldn't get it to work. And then they got it working like the third time. And the funny thing is, I think you would experience the most motion at nearest the poles, which means you should probably be messing with it the least. You know, and it wasn't just that they were messing with it and couldn't work. They got it initially working backwards and declared victory. Like, how do you do that? How do you say, hey, we got it going Great. The first time it's perfect. Oh, wait, shit. It's going backwards. But at least it was going perfectly, just backwards. This whole obsession with pendulums goes back hundreds of years. Like, it wasn't just Foucault and a pendulum. They were using pendulums prior to this guy for divination, for trying to detect the strength of gravity, not even joking.
Yep, but they completely ignore the Tamarack mines experiment.
That's a funny thing. Like they would take these pendulums and plumb lines, and they come up with all these excuses, like, you know, Earth's gravity field is different in places, and that's why we couldn't get perfectly plumb and level. And then they say, oh, it must be due to mountains. And then they go to the Himalayan mountains, and it deflects in the exact opposite direction than they predicted, according to them. So how do you get plumb lines? Like, you can't get up consistent plumb lines anywhere on a globe. But even then, like, we could completely absorb the plumb line deflections and curving plumb lines. We can completely absorb that, because you know what they do? They take that information and then they wrap that around a ball. That's basically what gravimeters are in gravimetry. Swinging pendulums. They got their pendulums, they got their dowsing rods. They're ready to do geological surveys, guys. Someone pack a Ouija board. Got your
Maybe a
tarot cards.
magic 8 ball.
Yep. Let's go. Let's do some geodesy. We're going to stare at the stars, do a little astrology. We'll get our plumb lines from the stars. I'm going to swing these pendulums, and we're going to ask the magic 8 ball if Earth is flat. That's what globe surveyors do, man. It's crazy. It's like, hey guys, let's measure some spherical excess today. Unlike all the other days, today we're actually not going to use any terrestrial refraction. We're just going to pretend that after all this time that it doesn't exist, because we're trying to measure spherical excess. All right, guys, get your theodolites out. You see your bubble level? We're going to pretend that that's perfectly level out to about 69 miles. Okay, and we normally would do a geodetic gravimetric correction here too, but like all the other days we've done it. But today we're not going to do that either, because we're trying to measure spherical excess. All right, so let's throw out some refraction. We're not using that. We're not using gravity field corrections. And we're going to pretend that that our bubble level's out to 69 miles. So we got perfectly plumb to horizontal that distance. All right, so now we're ready to measure curvature. And oh wait, shit, we can't do it? All right, well, let's do like 300 readings and keep only the best ones. By my calculations, we need to be dipped down at about half a degree. So let's keep all the ones that show about a half a degree dip, guys. All right, there, we just measured spherical excess. Like, you think I'm joking? That's exactly what they do.
Yeah, they probably measure to a standard rather than to an accuracy.
Yeah, it's how they know which of their observations they need to throw out. And then they keep all the others, and they do a root mean square. They do an average of what remains. And oh, holy shit, it confirms their bias. Guys, we just affirmed the consequent. That means we proved Earth is a ball. Now let's add back in refraction and curving plumb lines and deflecting verticals, and guess what happens? It's flat.
Yeah, I have to wonder how they're calculating their latitudes during the daytime without solar filters that they didn't have in the 19th century.
Oh yeah, doing sun observations that way. Yeah.
They stick a stick in the ground and measure that.
Yeah, like Eratosthenes. We have to assume parallel rays, guys, but don't worry. As long as we assume parallel rays, we don't have to measure that the Earth is actually curving. It's funny because the parallel rays assumption basically takes care of that. Once that is out, yeah, then they just rule out a flat Earth.
There's some claims out there that are made, which I can't verify to be true, and they're made by both globers and flat earthers alike, right? Such as, if you go south, directly south from any starting location, right? Like, choose Australia, choose Europe, choose Asia, anywhere, and go directly south, you will reach the coastline of Antarctica. That's a claim, and I don't know if it's true or not.
Yeah, isn't that claim also not exclusive to a globe?
Exactly. Right. That Eric DeBay makes that claim.
Right.
I'd like to know how he verified it.
And it wouldn't answer anything either way.
Yeah, it would answer some stuff.
Yeah, I was about to say, like, it would definitely give you more questions than you had before.
Right. Well, even if that's true, like, okay, so you go from the tip of South America and you reach a place, that's icy, and they say it's Antarctica, right? Okay. So now you leave the tip of South Africa and you go south, directly south, and you reach another icy area. How do you know that's Antarctica?
Right. Or how do you tell the difference between whether or not you are following lines of longitude that extend radially out from one point of origin, or if you're converging upon another point of origin along the same longitude?
Yeah, that's the thing it would answer.
Mm-hmm.
Yeah.
That's a good one. Yeah, good point. Yeah, yeah. How are you determining what is south? Are you using stars, the sun, a compass, magnetic field lines? Like, what are you using? How are you determining which way is south? Because we know about magnetic field fluctuations and declinations, inclinations. The magnetic field map that you post, Yoder, that's pretty messed up. It's pretty
Right, isn't
wonkily
that?
donkly.
It's one of my favorite maps. So I got an interesting piece of insight, not regarding that, but supposedly if you are under the equator, let's say you're under the equator, maybe you're biased a little to the north or to the south, just a bit. Let's say you could see basically on your right side, due right, you could see Polaris right on the horizon, hypothetically. You could travel west and keep going west, and Polaris will show no parallax, will not move.
Yeah, interesting. Yeah.
That's the claim. Right? So you could go whatever you want to call it, a great circle route, in which case the claim would be that you are curving down, or that you are going exactly 270 degrees west from 0 degrees latitude, and you are not turning at all. You're on a flat topology. Would Polaris not move the entire time? And then you think about like the UTM maps, the Universal Transverse Mercator maps. What do they depict? Well, if you were to plunk yourself down there on the equator on that map and head west, all the lines of longitude are orthogonal to latitude. Polaris would not move. You keep heading west, keep heading west. I mean, it's almost as if it was effectively an infinite distance and casting parallel light rays from the north. If you were to look to your left, and the Sigma Octantis region is a group of stars. I mean, those would also show similar characteristics, wouldn't they? I mean, that's the claim. That's not what I'm claiming, but that's what's claimed. And the way the globe explains this is you're curving down in a third dimension. Well, if that's the case, a gyroscope, like you should take one with you. You should watch as the housing rotates as you go underneath it, essentially. Right, because the inertial plane of the gyroscope would remain fixed. You'd set it up, maybe at eye level, you could say, just for sake of visual purposes. As you rotate down, as you go over the curvature of the Earth, as you go around the globe, you should be able to see that thing rotate, like the bottom of it. At some point, you should be looking up underneath it, right?
Right. Just as if
Nobody's-
you were going like over a hill with a gyroscope, right?
Yeah, exactly. You know, and nobody's ever been able to demonstrate that this is the case at all whatsoever at any time. So that's interesting. Now, is it possible on a flat Earth to do this without seeing the gyroscope move? And boom, 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 you end up back where you started again. So this is where some people like to plop open the map and then laugh at flat earthers and say, well, how did the Japanese get to Pearl Harbor, right? Because they're thinking of this UTM rectangular map where all the lines of longitude are orthogonal to latitude. They're perfectly vertical up and down, intersecting horizontal latitude. Not minding that this is still a globe map where you have a non-uniform scale. And the further you get to the top or the bottom of the map, those map distances between lines of longitude end up converging. So you got to reapply your scale. You got to take like your 1 inch is equal to 500 mile scale, and suddenly now it's 1 inch is equal to 5,000 miles, you know? But is that really happening? Like how much does it scale like that far north and far south? You know, and one of the reasons why these UTM maps, why they don't show 90 degrees north and 90 degrees south is because mathematically this projection puts those 2 points at infinity. So they'll stop. That's why you see these maps stop at like 80 or 85 degrees north and south. I mean, they can't go the full 90. 90 is infinity. You know, and it's worth bringing up too the pizza world map, the azimuthal equidistant map, like on the UN flag. The South Pole, that's still a globe map because the South Pole is now a ring and it's not a point. And if you apply the scale properly, like many people in this argument don't, if you're at 89 degrees south, just shy of the outermost edge of that AE map, that's actually like a 430 mile circumference, not like a 60,000 mile Captain Cook circumference. It's actually about 430 miles on that map. But is that really happening in real life? You know, it's interesting. I was reading some history of geodesy last week, and some of these French explorers that were sent by the crown, King Louis the whatever. Don't remember if it was the 4th, the 5th, the 7th, the 11th, 14th, whatever the hell. But some of these French scientists discovered, by their own accounts, their claims, that the stars don't rotate uniformly with distance traveled, that the further north you go, the more you have to travel for the stars to rotate the same degrees as before. So like Polaris, for example.
What other stuff can you tell me that's very interesting to convince me?
Okay, well, heliocentrism doesn't predict the tropical year. Do you know what I mean by the tropical year?
Heliocentrism is the globe model, right?
Yeah, in a solar system.
It doesn't predict the The seasons you said?
Yeah, a tropical year. So specifically, the sun migrates between the Tropic of Cancer and the Tropic of Capricorn in the sky.
Mm-hmm.
So if I
Uh,
were to go out on let's say let's pick the winter solstice. Wherever winter solstice is for you on the earth, it doesn't matter. If I were to drive a stick into the ground and if I were to measure the shadow at noon, noon at this case not being your time set by your local government, but in this case, the zenith, the highest point in the sky that the sun goes. And I were to mark the point on the ground where that shadow is, I could count 365 days until the sun returns to that same point and produces the same shadow length, marking that same spot on the ground. Fantastic. So I can do this again the next year. So I have that same spot marked on the ground, and I will count 365 sun ups and sun downs. And
at
over
the
those
same hour.
365 days, I will watch the sun migrate from the winter solstice to the equinox, which is the equator, to the summer
You're
solstice,
saying
back to the equator. I'm almost done. And then back to your winter solstice. Again, 365 days. I will do this at third year, okay? I'm almost done. Third year, I will also count 365 days until the sun returns to that same spot, marking a shadow at the same spot on the ground. But on the fourth year, if I wait 365 days, I haven't waited enough. I have to wait one more day for that sun to return to where it was. This happens every 4 years. This is not a difference between solar and sidereal globe orbits around a sun. This is an actual extra sun up and sun down that occurs every 4 years, and it's not on the leap year.
in the fourth year you had to wait how much?
One
One
extra
more.
day for the sun to produce a shadow to hit the same spot on the ground that I had marked the
That's
last 3 years.
interesting. What
Yeah.
about, so are people saying that we have winter because the sun is far away during winter? And that's why the planet gets cold or something like that?
Yeah, but under the
What the,
heliocentric globe model, the Earth is actually closer to the sun in the winter. I bet you didn't know that.
no, but wouldn't it be interesting in order to test this that people do something that you said but not like that? Instead of that, measure the measure the shadow distance from the sun uh, in the summer but also in the winter at the same hour. You know what I mean?
Yeah.
Because I would assume the sun, if it's further away, the shadow should be longer at the same hour, no?
Not necessarily, no.
I mean, according to the Helios, what do you call it? Heliocentric
Yeah,
model.
helio meaning sun centric.
Yeah. Also, the thing. So, do you agree with this? You agree that it should be that way according to the heliocentric model?
Well, what is granted to us from space agencies, from astronomers, is that the sun does occupy the relative center of the solar system, and that during the winter, Earth's irregular orbit around the sun puts the Earth slightly closer, about 3% closer to the sun during the cold season. Right? But it's warm for the Aussies
Mm.
right? So winter for us. So this being in the northern climates, December through February, freezing cold. But the claim is that Earth is also still closer. Now, our friends in Australia and New Zealand, they're probably roasting their asses off meanwhile. So for them, that just seems normal. Like, okay, yeah, it makes sense. The Earth is closer to the sun. I'm getting a sunburn out here, and it's freaking January. It's still a trip for me to think about, though. I've never been down there.
You mean you've never been upside down?
Nope, never been upside down, my friend.
Well, regarding, going back to the Antarctica thing, right? Some people point out, now, I don't know, but some people point out that, okay, so shouldn't it just be like, especially if we're actually closer within that solar system model, right? If the north melts and then refreezes, why doesn't the south do that too
Yeah,
Right.
that's what
during its
we
summer
were
and winter?
talking about. Yeah.
That's a good point because you not only have Earth's tilt so called working in its favor, but you have the proximity working in its favor too. You're exactly right. I never thought of that before.
Well, I thought you were talking about that when you were talking about Australia being. I thought.
He's talking about Antarctica. So listen, the point is if Earth is a globe and it's closer to the sun during the southern climate's winter, and if the globe is tilted towards the sun during that same time period, then why hasn't Antarctica melted? Why doesn't it go through a similar cycle as the Arctic region in the extreme north?
Wow, that's a good question. Let's see right now. Let's see.
I think you'll find that they say that to a degree it does, but overall the mainland, right, the covered parts of land stay frozen to a large degree, but some of the
Yeah.
outskirts do melt. So that's why they choose to go there in the summer with their big ships and that, because there's
Yeah, they
less
show.
ice in the waters to negotiate, less glaciers.
They say it's
But
melting. Yeah.
right, but if you look on Google Earth, like Google Earth depicts the Arctic region as just ocean, no ice at all. And then other
Look, this
pictures you
is
get from
so.
aerial views, there's a lot of ice. So it's like, okay, so it melts, completely melts during its summer in the north, and then glaciers form in the colder weather. I don't know. That's weird.